So when you have a weak acid, such as, again, they very commonly like to use HA as a weak acid. And when it acts as an acid, it creates an equilibrium system. And yeah, I'm using water this time just to kind of show you. Okay, it creates an equilibrium system where, again, you have mostly this and very, very little of this. Okay, and let's give it a Ka value of 1.2 times 10 to the minus fifth. Okay, we know that when a weak acid, or any acid, creates an acid-base reaction, we know that over here, this creates the conjugate base. Okay, and a conjugate base, even though this is a weak acid, and therefore this is a stronger conjugate base, theoretically, okay, that conjugate base also can create an equilibrium system. Okay, so a weak acid creates an equilibrium system where it has a Ka value. A weak base also creates an equilibrium system where it reacts to reform that acid and also some hydroxide, okay? And when that does that, that's going to have a Kb value. Okay, now notice a couple things here. Number one, notice it's not the same equation in reverse. In both cases, when a weak acid or a weak base acts as a weak acid or a weak base, the reaction always involves it reacting with water. Okay, notice it's not A minus reacting with H3O plus. Okay, it's A minus reacting with H2O to reform the acid and then also to produce some hydroxide ions. And again, that's what makes it basic, is that those hydroxide ions in there. Okay, and when that happens, when you have an acid that has a Ka value, and you also have its conjugate base, which can also act obviously as a base to reform the acid, in a different chemical equation, there's a relationship between their Ka and Kb values, okay? In that the Ka of the acid times the Kb of the base is equal to 1 times 10 to the minus 14th. It kind of goes back to the pH scale, where pH equals, the pH scale goes from 0 to 14, kind of that same concept. Okay, and if you take the negative log of both of those, we know we get the pKa, and you can also have a pKb. The pKa plus the pKb is equal to, big surprise, 14, just like the POH plus the POH is also equal to 14. So if we're given this equation here, where a weak acid creates a conjugate base, and we know the Ka value, and then they say, okay, what's the Kb value for that conjugate base when it acts like a base reacting with water to reform the acid and to produce hydroxide ions? Well, we would just have to take 1 times 10 to the minus 14th and divide by the Ka value, 1.2 times 10 to the minus 5th. So 1 times 10 to the minus 14th divided by 1.2 times 10 to the negative 5th is equal to 8.3 times 10 to the minus 10th. Okay? And what that does is it shows you that in this case, actually, this acid, the HA, is a stronger acid than A minus is a base, because you've got a much larger value for the Ka value than you do for the Kb value. So a weak base acts just like the Kb expression. Again, obviously the B stands for base. It's when any weak base, which again, they would tell you, they don't expect you to know what all the weak acids and weak bases are. They would tell you, they would say ammonia, NH3, is a weak base, blah, 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 blah. And notice when something acts as a weak base, it reacts with water. Again, it's not the reverse of this reaction. It's not the conjugate base of the weak acid reacting with the acid. That's not what a base does. A base is something that when you put it into water, it creates hydroxide ions. Okay, so whether that's a weak or a strong base like NaOH, you put that into water, what does it do? Not even an equilibrium system. You get hydroxide ions. Well, a weak base does the same thing by, again, reacting with the water, you could say, to create, again, the molecular form of the acid, and then, again, some hydroxide ions. Okay, but the Ka and the Kb are not the same equation, just in reverse. They are separate equations where in both cases the weak acid and the weak base are both reacting with water. So here we can see it as well. What does the base do? Again, we can say it creates hydroxide ions, but the Bronsted-Lowry definition says what does a base do? It accepts a hydrogen ion. So this one of these H's is going to come here to create NH4+, and then of the H2O, what are you left with? You're left with the hydroxide. Okay? So we do create an equilibrium system, so we do have to set up the Kb expression. Now, just like with a weak acid, though, the concentration of the conjugate acid and then the conjugate base are going to equal each other. Okay, for every one NH4+ you get, you're going to get one OH minus. So whatever the hydroxide ion is, or whatever the concentration of the conjugate base is, they're going to equal each other. So just like when we did Ka and we said it's the hydrogen ion concentration squared, because the H plus is the same as the A minus, okay, over the concentration of HA. Same thing here. The concentration of hydroxide or NH4 plus squared, or X, a lot of times that's going to be an X squared, over the concentration of the original conjugate, or the original base that you started with. And obviously we leave water out because it's a liquid. Okay, and then of course if you take the pKa, you take the negative log of the Ka, you get the pKa. If you take the negative log of the Kb, you get the pKb. Again, up here, this is kind of the important part about pKa and pKb, is that when you add them together, you do end up getting, just like pH plus pOH, it does add up to 14. Okay, so if ammonia has a pKb of 4.75, what is its Kb? So again, to get pKb, we take the negative log of the Kb. So to go backwards, if we know the pKb, we have to go 10 to the negative 4.75. Just like with pH, you got to take 10 to the negative pH to get to the hydrogen ion concentration. So 10 to the power of negative 4.75 equals, put that into scientific notation for me, the Kb is going to equal 1.78 times 10 to the minus fifth. Okay? And again, in this case, if ammonia, on a test, they would say if ammonia, comma, a weak base, if methylamine, comma, a weak base, has a Kb of 4.38 times 10 to the minus fourth, what's the pKb? Okay, so again, in that case, you would take the pKb is just going to equal the negative log of the Kb value, so 4.38 times 10 to the minus fourth. So we're going to go negative log 4.38 times 10 to the minus fourth is equal to, and again, similar to pH, when you're estimating the pH and you know the hydrogen ion concentration, since that's the negative fourth, we know the pKb is going to be somewhere between 3 and 4, and it is. It's 3.36. Okay, example 3, which is the stronger base, ammonia or methylamine? So based on the Kb values, we've got a Kb of something to the negative fifth and something to the negative fourth. And again, the bigger the number, just like with acids, the bigger the Ka value, the stronger the acid. The larger the Kb value, the stronger the base. So since this one's only to the negative fourth, methylamine is the stronger of the two bases. Okay, what generalization can you make about the value of the Kb and the strength of the base? Again, just like Ka, the larger, the greater the Kb, the stronger the base. Okay, and then in terms of pKb, just like pKa, here, remember, this one's the stronger one. Just like with acids, the smaller the pH, the stronger the acid is. The smaller the pKa, the stronger the acid is. Therefore, the smaller the pKb, the stronger the base is. Okay, so the smaller the pKb, the stronger the base, just like with pKa. Okay, example 4. What is the pH of a 0.44 molar solution of ammonia? Okay, so we do need to use some of this earlier information. We know that the Kb of ammonia is 1.78 times 10 to the minus fifth. So 1.78 times 10 to the minus fifth is going to equal, now remember ammonia, we saw the equation earlier, becomes NH4 plus and OH minus. And remember, the pH is based on the hydrogen ion concentration, okay, which means the hydrogen ion concentration is going to be based on the hydroxide ion concentration. So without doing an ice table, we know this one's going to be X, this one's going to be X, this is going to be 0.44 minus X. And so again, to make the math easier, we're going to go X squared over 0.44. Okay, and now we're going to solve for X, and that's going to give us, again, even though we made this assumption here, it's going to give us a number really, really close to the actual hydroxide ion concentration. So 1.78 times 10 to the minus fifth times 0.44. And then I'm going to take the square root of that answer. And X, which again is equal to the concentration of NH4 plus, and it's also equal to the concentration of OH minus, which is the one we care about, is 2.80 times 10 to the minus third. Okay, and now to get to the pH, there's a couple of different ways you can do this. You can get the pOH is one way to do it. So pOH is the negative log of that answer is 2.55, and then the pH, and again, I would show that. I would show taking the negative log of that 2.8 times 10 to the minus 3. And then the pH is going to equal 14 minus 2.55. So 14 minus that answer equals, let's try to put it in scientific notation, 11.45 would be our final answer. Okay, example 5. Calculate the Kb value of a 0.1 molar solution of a weak base with a hydroxide ion concentration of 1.75 times 10 to the minus third. So Kb is going to equal, again, we don't know what the weak base is, but we know that, again, whatever it is, it's going to react with water to form a conjugate acid and hydroxide. And we know that the hydroxide is going to have the same concentration as that conjugate acid. So we're going to take 1.75 times 10 to the minus third and square it. And then we're going to go 0.100 instead of minus X. Remember, when it's a real number, put the number in there. So it's a 0.1 molar solution, but enough of it dissociates to create a concentration of 1.75 times 10 to the minus third. So subtract that. So 1.75 times 10 to the minus third squared, because again, the hydroxide ion concentration is equal to the concentration of whatever the conjugate acid is. Okay, so there's two of them on the top, just like NH4 plus in this case, if it was NH3. Okay, and then we're going to divide that by 0.1 minus 1.75 times 10 to the minus third equals, in scientific notation, a Kb value of 3.12 times 10 to the minus fifth is what I get for that one. Okay, and then our final one, calculate the Kb of a 0.250 molar weak base solution with a pH of 9.12. So if the pH is 9.12, now this last one I went from hydroxide to pOH to pH. I'm not going to do it that. I'll do it the other way this time. So I can say, okay, if the pH is 9.12, then the hydrogen ion concentration is equal to 10 to the negative 9.12. So 10 to the power of negative 9.12 equals 7.59 times 10 to the negative 10th. And then to go from hydrogen to hydroxide, because it's a weak base, we're going to take 1 times 10 to the minus 14th. Remember that H plus times OH minus equals 1 times 10 to the minus 14th. Just like Ka times Kb. Okay, so I can go 1 times 10 to the minus 14th divided by that answer I just had, and that gives me a hydroxide ion concentration. And again, it doesn't tell you what the weak base is, so it doesn't matter. So a hydroxide ion concentration, and I'm just going to put a conjugate acid concentration of 1.32 times 10 to the minus 5th. Okay, so if we're going to calculate the Kb value, it's the concentration of hydroxide and the conjugate base on the top squared over the concentration of the weak base subtracting, and again, it's not going to make any difference because notice that minus, it's so small that you're not going to see any difference in the answer, but you still should show it, and you still should put it in your calculator. Again, you might as well. So 1.32 times 10 to the minus 5th squared divided by parentheses 0.250 minus 1.32 times 10 to the minus 5th. Close those parentheses. Hit equals 6.97 times 10 to the negative 10th. Okay, and that is, again, Kb very, very similar to Ka. It's when a weak acid, or a weak base, is added to water where it creates a conjugate acid and then hydroxide ions.